In the last session, we designed memory modules in VHDL and we learned how to code single port RAM and dual port RAM. Now let's talk about finite state machines in VHDL. We will discuss what is finite state machines, why they are important, and how they works in VHDL. So let's start. This is a simple example of a finite state machine system. In this example, we have this heating system like in your geyser, etc. So let's see how you can develop this using finite state machines. We will look on different states and their transitions. So from this diagram, we see that we have three different states. These are idle, heating, and ready. So it is quite simple. Idle means nothing is happening. Heating means heater is on, and ready means hot water is ready for use and heater is off. So let's say our initial state is idle, means you have just powered on your heater, and at that moment heater is off and indicator LEDs are also off. You can say this is our default state as well. Now you pressed on switch, and when it is pressed, your heater should start heating, right? Means heater will on and indicator LED will also on. So this transaction will happen. So this is our second state. Here heater is on and red LED is also on. And we got our first transactions when you pressed your on switch. So when we are at this state, we can have two options, right? Either you can switch off your heater at any point of time, or your heater reaches at the desired temperature. So when you switch off your geyser, say it returns to its default state, means this transaction is happening. And if the desired temperature is reached, then you defined one additional state for that, which is ready state. At this state, heater is off and ready LED indicator is on, means water is ready for you to take a bath now. Okay, so if temperature is reached at desired temperature, then this transaction will happen. Now, if you take a bath, then you want to switch off your geyser, right? So you made this transaction as well. Means when switch is released, it goes to the idle state again. Now you can also add one more transaction from ready state to heating state, right? For example, if temperature goes below some threshold, then you want to turn on your heater again, right? So you can add this transaction as well. Although I have not configured this transaction here, just to explain that how easy it is to make improvements further if you are using finite state machines. If there is something in your mind to improve the system or you have feedback from your end users, you can deploy them very easily using finite state machines. So this is the benefit of finite state machines. I hope you understand it little. What is finite state machine? So it have many states and you define those states and the transitions between them as well. And their states are finite, means you define each of your state. That is why it is called finite state machines. Okay, so let's develop this simple finite state machine model in VHDL. So this is our library declaration section and entity declaration section. Let's start by declaring the libraries and packages. So they are library IEEE use IEEE dot std underscore logic underscore 1164 dot all semicolon. Now declare entity section. So this is our entity. Entity heater FSM is port clock in std logic, reset in std logic, switch in std logic, temperature in std logic, heater out std logic, red LED out std logic, green LED out std logic bracket close semicolon and entity semicolon. So clock and reset are mandatory in finite state machines because FSM is a synchronized system and it is synchronized with your clock. Means every transition will occur at clock edge only. Other are all input output ports, depends on your project requirement. So for this project, we have switch and temperature meter as an input port, and heater, red LED and green LED are our output ports. So everything is very clear from the last FSM diagram. We have switch input to turn on or off your heater, temp or temperature sensor to detect your current temperature so that if it is matched, we can change our state. And we have indicator LEDs like red LED and green LED as an output. So we explain this that what they indicates, right? Like red LED means heater is on, green LED means you are at ready state or heater is ready. So this is our entity section. And next is architecture section. In this slide, we start our architecture and we define one new data type, which is having all of our state, means idle state, heating state, and ready state. Name of this custom data type is FSM state type, and we have one signal from this data type. So our VHDL code for this section is architecture, behave of heater FSM is type, FSM state type is idle, heating ready semicolon, signal state, FSM state type semicolon. Now begin. Next, we will code our main functioning. So this is our architecture and our functioning start from this begin keyword. First, we have registered process block. So we have reset and clock in the sensitivity list. Next, we have reset condition first, or your initialized condition, you can say. So all the outputs are turned off, like heater is off and LED indicators are off. Now we are also saying that we are at idle state when reset is given, and that's fair, right? And this is really important, just in case your system malfunctioning due to any reason, or while developing your system, if there is some logical error in your design and it is stuck at some infinite loop or state from where it is not going anywhere, so you can use this reset feature to jump to the default state. So this is very important to do. So we have our VHDL code like this. FSM process colon process reset comma clock begin. If reset equals to 1, then green LED gets the value of 0, red LED is 0, heater is 0, and state is ideal. Else if at rising edge of clock, then. Now we will write our state machines from rising edge of clock so that everything is synchronized with timing and clock cycles. So we have this condition, else if rising edge of clock, then. Now the easiest way of designing finite state machine is case statement. Why? Because at any point of time, you will be at one state only. So you will always have only one case to select. So each choice of case statement will define your current state, and you will write all the operations you want to do at that state. Also, you will specify that what will be your next state as well. Because if you do not define that, then you will stuck at the one single state. Now let me quickly read this state machine code in VHDL. Then we will explain it. So it is case state is when idle, green LED is 0, red LED is 0, heater is 0, and now next state definition. If switch equals to 1, then state is heating, and if when heating, red LED is 1, heater is 1, if switch equals to 0, then state is idle. Else if temp equals to 1, then state is ready, and if when ready, red LED is 0, green LED 1, heater is 0, and if switch equals to 0, then state is idle, and if. Now when others, state is idle, and case. So first is idle state. This is also the default state of our system. At this state, heater is off and red LED and green LED also off. Means we'll state all of our possible outputs at this state. Now we will tell that what will be the next state and when. So from our state machine diagram, we said when input switch is pressed, then it will go to the heating state, right? So we have this condition that if switch equals to 1, then state is heating. And if, well, you can write this state transition here like it is written, but you can also write them in a separate process block. Means one process block will drive your outputs and results, and another process block will direct your state transitions. Both methods will work fine, so you can choose any method. If you feel writing everything in one process block is complex, then you can split them in a separate process block. Now coming back, so we said if switch is pressed, then the new state will be heating. So define this heating state. Means when heating, red LED is 1, heater is 1. If switch equals to 0, then state is idle. Else if temp is equals to 1, then state is ready. And if. Now we monitor the switch input to detect if the user activates the system by pressing it or not. So at this state, heater will on, red LED indicator will turn on, and you can also mention that green LED is off. So outputs and results are defined for this state. Now specify that what will be your next state. So from the last finite state machine diagram, we can have two transitions from this state. First, when you switch off your heater, and second is when your desired temperature is met. So we write this condition. If switch is equals to 0, then state is idle. Else if temp is equals to 1, then state is ready. And if. So this is clear that if you release the switch button, then you will go to the idle state. And if the temperature is reached to the desired temperature, then the next state will be ready. You should also specify your third transition here. When switch is not released and when your desired temperature is not met. So at this point, we should stick at this state only. Means at this condition, your next state will be heating state itself. This is called self-state transition. Although I have not written that just to make it simple at the moment. Now let's define ready state. So when ready, red LED is 0, green LED is 1, and your heater is 0. If switch equals to 0, then state is idle. And if. In this ready state, the red LED is turned off and the green LED is turned on. The heater is also turned off at this ready state because the desired temperature has been reached already. So now you can guess that at this state, red LED is off, heater is off, and green LED is on. So these all are our outputs at this state. Now define your next state. So it has only one transitions in our state machine. That is when you release the switch, then it will go back to your idle state. So simply write this with the if condition that if switch equals to 0, then state is idle. That's it. If you have more transitions, as I said, to go back to the heating state when your temperature goes below some threshold, that you can also add that transitions here as well. You may want to try that by yourself, then please try. You can take one additional input to input that what is your lower threshold, or simply take some offset from your desired temperature or percentage offset from your desired temperature, depending on your thought process. For example, you take offset of 10 degree. Then if you set your desired temperature at 60 degree, so when it will reaches at 60 minus 10 means 50 degree, it will jump to the heating state again. Same you can say that 10% of your desired temperature. So it depends that how you want to build it. Now coming back to our code. So in the last we have this others condition, and we said that at this scenario state will be idle. Note that other section is mandate with case statement. Does not matter that it is doing something specific or not. So it is here. And as a good practice, Always include a when others statement in your state machines to return to a known state. And it will help you when your state machines or your design goes into some invalid state. Now, you might question that how a simple state machine could enter into an invalid state, right? Well, in simulation, you may not encounter that if you are specifying all the states and all the possible transitions. Means I'm talking about the perfect design. But still, in real life or in actual hardware, there are many factors which can trigger these situations because you can have a robust logic and error free design, but you cannot control external issues like environmental issues or hardware failures, etc. For example, hardware related issues like power glitches, clock signal problem, timing violation, or power supply fluctuations. So these may trigger some random state which may not well defined in your system. Environment thing can be temperature of environment, humidity, etc., which can also trigger some random state. And from that state, if it is not meeting any condition to select the next state, or even just your product even not doing its operation, then issues can be anything. So in such events, this when other conditions covers everything for you. Now finally terminate the process block and architecture section of our VHDL code. And that's it. Your design is complete with a finite state machine system. Now it's time for some tips and quick recap. So finite state machines can help you in optimal design and functionality. Always design a state machine with a registered process. This will cover your transition issues and your design will always synchronize with your clock signal. Another reason of using register process is that state machine requires memory. So register process stores that state information in the flip-flops. Always give reset condition to ensure that your state machine can return to its default state. And it will also provide a well-known starting point for your designs. Next, try to define enumerated data types and list all the valid states of your state machines. Like we did for our example, we define idle state, heating state, ready state, like that. So each state is very clear that what it is and what it will do. Note that it will not add any additional hardware in your FPGA. This is just simplified code, and your synthesis tool is well developed to handle that in hardware. Just think that what if you have states like 0, 1, 2, and 3? Like 0 means idle, 1 means heating, 2 means ready, like that. How it sounds? Very bad, right? And it is not easily readable as well. So simply define them with the relevant and meaningful names. And in the background, your tool will figure out that how to decode it into a digital codes like 00 for idle, 01 for heating, etc. And trust me, it will reduce your chances of errors as well. And others can also understand your code very easily. Next, always use a case statement for any action against each state and also for defining your next state as well. So try to avoid using if else statement as they can create priority decoders in your hardware and this can create inefficiencies in your designs. Like we explained in the previous sessions that how they are inefficient and how they degrade your hardware performances. As I said, you can split your code between two separate register process blocks for defining the output of each state and defining the next state. Otherwise, you can also combine both things into a one register process block, like we did in our example. If you feel that complex, then simply split it into two register process block and it will not impact any hardware performance and it will easy to read as well. So both ways are completely fine. Finally, always include a when other condition and use that for your reset transactions as well. And it will protect your design from logical glitches or hardware glitches or real life unwanted conditions. Okay, so that's it for today. Hope you are clear with the finite state machines and now you know that what are finite state machines, how they works and how to design them in VHDL, and what are the good practices. In the next session, we will be telling some important tips and tricks and good practices for FPG designs and VHDL designs. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.